Hello everybody, welcome to the virtual lab about solar PV. It's my pleasure to start virtual lab using Matlab Simulink, but I prefer to spend about the first 15 minutes to review the modeling and driving equation of the solar PV panels, and after this one I will explain about the Simulink software, Matlab, and then I will show you how it's possible to implement the equations and find out the power versus voltage and current versus voltage in the solar PV. Here I would like to explain about the current voltage characteristics of a photovoltaic solar panel. The most important point that I would like to explain about the photovoltaic solar panel is that we need keep in our mind that photovoltaic solar panel is a current source and it is not a voltage source. Then we should keep it in our mind always that we face with a current source, then we can expect the behavior which is related to the current source. In the lab, it's possible to show these characteristics, this relationship between the current draws from the photovoltaic solar cell and its voltage across of its output terminal. It's obvious that current is proportional to the irradiance to the module. It means that when the solar density increases, the current will increase too. The generated current will increase. However, voltage is not changed appreciably by irradiance and is limited by the maximum cell voltage of 0.6 volt. In our lab activity, which is simulation, or in the real application, real measurement, we can draw the relationship between the amps and voltage in the different solar intensity. Now, I would like to explain about the modeling of the multicrystalline photovoltaic solar. As you can find here, a simple model of the photovoltaic solar panel can be considered as a current source which is parallel with a diode. And in a simple form, we can find that the current draws from the solar panel is equal to IPH, which is generated by the solar cell itself, minus ID, the current which will goes toward the diode. However, a realistic model of this one includes another two resistance, RS and RP. RS is due to losses by Joule effect. This is due to metal grids, semiconductor materials, and collecting bus. And RP, which is a shunt resistance, is due to the leakage of a current due to cell thicknesses and surface effects. Then, in the realistic model, we have RS and RP, and we cannot ignore them. Now, the point is that in our modeling, we would like to find out the relationship between the current and voltage. As we can find here, IV equation for Shockley diode is a simple model and more realistic model. ID is equal to, as you can find it here, is equal to IS and times exponential or e power QVOC divided by NSKA T0 minus 1. And since VOC is the open circuit across of this photovoltaic panel can be considered as it's equal to V plus RIS. Then if we substitute VOC as a V plus IRS, our modeling equation can be written as follows. Then I, if we substitute ID in this equation, we can write I is equal to IPH minus IS times exponential value of QVOC divided by NSKA or TO minus 1. This is a temperature. I will explain all of these constants in the next slides. Then we can find that I has this relationship with V. Now we should be able to draw the relationship between V and I. As I explained it in the previous slides, we have the relationship between I, the output current of the photovoltaic solar cell, and the voltage. However, there are some other constants that if we have them, we can find out and we can complete the relationship between the I and V. In this table, we can find some of these constant value. Now, as you can look, we have K, we have A, we have operating temperature, we have RS, but we don't know IPH, we don't know IS, and by considering these coefficients that we know them, the unknowns become the unknowns is only IPH and IS. If we know these two, it means that we know the relationship between the voltage and current that it's appeared in the two sides of these equations. Now, if we have a series of cells, the number of the cells that there are series together can be considered as an NS. But if we have a parallel rows of this series, the number of the parallel rows together is considered as an NP. Now, I is equal to NP times IPH minus NP times IS and times this bracket. Now we should find out how is possible to find out IPH and IS. IPH is proportional to the incidence flux and a temperature, but it is independent from voltage or RS. Then, based on the experiment, they found that IPH is equal to ISC, which is a short circuit current. You can find it here in the table, short circuit current. For example, for this solar PV module, it is equal to 9.06 ampere. You can replace it here. Plus Ki, which is a constant cell short circuit current. It's here, it's a 0.058% per degree centigrade. Times it's a temperature, operating temperature in the absolute operating temperature minus reference temperature, which is a room temperature, times the fraction or the ratio between G to reference G. What is G? G is the solar irradiance that we have right now, and we would like to measure the relationship between voltage and current at this G. G reference is the solar radiance at the standard condition that, as I explained it before, it is equal to 1000. Then by knowing this one, only again we have IPH. ISC was saturation current, and now we are looking for IS. We find IPH, now we are looking for IS. IS can be calculated from this equation, which is equal to IRS. IRS is the reverse saturation current. We don't know this one. Times this ratio of the temperature times this bracket, which is the exponential function. All of them are known. EG is the energy band gap, and it will be announced by the manufacturer in the data sheet of the or in the catalog of the photovoltaic solar, and the Q is a constant. As you can find here, IS is proportional to IRS, and IRS itself can be found from this equation, which is equal to ISC divided by exponential function of Q VOC divided by NSKATO minus 1. This is IRS. Then, by knowing IRS and replacing here, we will find IS. By having IS and by having IPH, easily we can find out the relationship between the I and voltage. K also is a constant that we are using in all of these applications. As I explained it before, the relationship between the current and voltage can be found in this configuration. Normally, for a constant current, in the special voltage, the current will drop. But what I would like to explain here is the effect of the temperature or operating temperature of the PV solar panels on the behavior of the current versus voltage or the characteristics of the PV solar panels. As you can find here, by increasing the temperature, you can find that in earlier or smaller voltage, the reduction of the current will happen. It's obvious that by decreasing the operational temperature, the performance of the panel will increase. Then, always we should try to reduce the temperature to enhance the efficiency of the panel. Efficiency drop about 0.5% per each degree centigrade, and maximum design voltage is calculated for the lowest expected temperature. Now, if you would like to do the simulation for any PV array, and if you would like to use the Simulink, it's required to mention that normally PV array itself is one of the predefined modules that you can find it in the Simulink. But the fact is that if I use this PV array which is available in the Simulink, I cannot explain for you that how the behavior of the PV panels depends on to the different variables. Because of this, in my lab activities, I would like to prefer to use the normal techniques and using the subsystems in the Simulink in order to make this PV array by myself. Then, if you consider in the modeling of the solar panel, as I explained it before, we can consider this one as a one current source which is parallel to the one diode, and it's parallel to one resistance and series with one resistance which we call it RS. After opening Matlab, you will find that we have the Matlab environment like this shape. We have something like a command window that normally for typing any command you can use this area. We have one area which is called workspace, and the other side is the current folder that you can find all of them in the environment of the Matlab. Now you would like to use the Simulink in order to solve the equations in the Simulink 1. As you can find here, this is a Matlab version 2019A, and the Simulink you can find in the top bar that all of the icons are available. One of them is Simulink. I press on the Simulink, you can find that there is something like the different blocks that you can find it here. The first one is the blank model. There are blank library, blank projects, many things, many options that you have. I am selecting if I want to run the new project and new model, then I'm opening this blank model in order to create a new model. Then you will find that this is your model and we can save it under a name. This is called any name that you would like. Then you should open it. I will save it on the desktop. You can find it here in my course. I will go to the lab activities and I will call it, for example, recording PV, and I will keep it recording PV. Then I will save this one. Then there is a problem. You can find it here that it's not valid model name because it's not valid MATLAB function name. It's correct. Why? Because I use this dash line here. Then I will say OK and I will save it again. But this time I will remove this dash PV recording and I can add pre-record. Oh, I did a mistake. Okay, no problem. I call it recording PV1. It is saved as a recording PV1. Okay, I will keep it. Now I would like to make and to solve these equations that I mentioned here for you. In order to solve this equation by using there are PV modeling equation and using the subsystem, and in the multicrystalline PV solar panels that we have this type of the equations. Look, we have this series of equations and we would like to find out the relationship between voltage and current and power versus voltage. Now look, I would like to use the Simulink, and as I explained it, I save it under the recording PV. Now there is something that I would like to show here is the library. If you click on the library, you will find most of the toolboxes that are available here. Look, we have a commonly used blocks that normally bus creator, constants, discrete time integrator, all of them that are used in a normal programming, in normal Simulink, they are available here. But you can find a lot of the other things like the continuous function, like derivative, like integrator. All of them are in the S domain. If you are looking, this is state space, this is a PID controller. All of them are state space one. All of them are using the Laplace transformations. There is a dashboard. In a dashboard, you can find a lot of display that you are using the front panels. All of them are here. These continuities, you can find many functions that are using like saturations, and you can find them here. Then the next one is for the discrete domain. Discrete domain, it means that you are using the Z transformation. In the continuous one, we are using Laplace transformation or S transformation, which is the frequency one. But this is using in the discrete one or a digital one, we are using the discrete transformation, which is a Z transformation based on the honor of the Professor Zadeh. The next one is a logic and bit operations. Then you can find it here, all of them. This is a lookup table, math operations. Math operations is one of those that you are using frequently. You have divide, you have assignment, bias, add, absolute, and math function. You can define, I will open this one for you just to show you the math function. Just I will bring it for you to find and to open, and you see that there is a lot of function that you can use it, and this math function is very useful one, and you can use it different. For example, exponential function, logarithmic, come down, all of them are available here. Each of them you can select it. Then I'm not using, just I would like to show you that this type of the function are already available in the Simulink. All of them are here. You can use them. The gains, square root of something, sine, all are subtract, sum, everything are available. The other one is model verification. The other one is model wide ultimates. Ports are very important. Normally we have input and we have output, that, or we have subsystems that you can find it here. Subsystems, signal attributes, all of them are here. Convert میشه. This is signal routing. That's we can, this is go to something or from something. We can assign any number to a variable here by using the from or by using the go to. All of them are available in the signal routing. In the sinks you can find a lot of this sync. In order to display something, you can use oscilloscope, you can use XY graph, you can save the output for your workspace that I explained it here. This is a workspace. All the data output from the Simulink will be gathered in your workspace in the Matlab file, in the Matlab environment. Then this is a source. In the source you can find a lot of function that can be act as an input, like sine, like a step. All are here, like ramp, input, all of them are here. This is a string types. There are user-defined function. Most of the function that you cannot find it in the math operations, you can define it here, and they are already defined. And there's additional math discrete one and a quick insert. All are here that you can use them. Now we would like to start in order to find, but for this activity normally we need to have some subsystems. In the subsystems, as you can find it here, I need to make one PV array. Then in a recording of a PV array, because I want to model the PV array, I will make one block which is called PV array. Then I will write, this is the, I will go to this one, this is subsystem. In the subsystem we will open this one. Then in the subsystem we have one, we will put it there inside, and then we will open this. Then we have this subsystem. But before that I go to this subsystem, I will change its name to the PV array. Normally in the subsystem we have one module like this one. We have one array, we have one PV module. In this PV module we have some input for this one. It means that we need to assign some input to this, like for example, what is the operating temperature, what is the RS, what is the number of the series of the cells, NS, how many rows are parallel together, NP, what is the solar irradiation for these solar cells, what is the short circuit current of this one, what is the open circuit of this cell, and all of them should be inserted as an input, and we can find some of them in the manufacturer datasheet or manufacturer catalogs. Then this is our PV array. But now I would like to solve the equations by these subsystems. Then normally we will define, now we have in each PV array, as you can find here, it's a recording PV one, it's a Simulink file, and this is a PV array. In the PV array, as you can find here, we have some kind of the equations. All of these equations are used in order to make the PV array. The first one is TO is equal to TOC plus 273. T reference is 25 plus 273.50. It's related to the thermal part of the solar PV panels. Then I will make one subsection or subsystems, which is called, again, I will go to the library, I will select a subsystem again, and I will put it here. And this time I will call it thermal subsections. I will go through the thermal subsections and I will try to make these equations that are governing the PV modeling. Then the first one that we can find it here is that we need to make this equation. How? Very simple. We are going to the Simulink. Then I need some constant value, and also we need some kind of the input and output. Then in this one I will go through the constant. I will go through the constant. I can type it here, or I can go through these Simulink modules that you can find it here. For example, this one is a constant one. I will drag it and put it here. This is my constant, and this is one part. Okay. What is the first constant? It's a 273.17, which was written in OR. Then I will draw it in this way. Okay. Now I will use the mathematical. What is this one? This is a mathematical operation, math operation. In the math operations, I can use the add. I will add. Okay. Then what is the next one? I need one input. This is the, as you can find it here in the Word and the PDF file, this is TOC. It's the temperature in the centigrade. Okay, we need some input. Then to have this input from outside, then we will select just to have go to block. I will find the go to block because we need something to send it. Okay, what's its name? Its name is temperature, operating temperature in centigrade degree. Then I will press it. See now. Okay, then very simple. I will connect them together. Oh, then I have this one. Then I should show this one in my one variable in the output. Then I am using the from block. In the from block we can find it here. Then this is a go-to that is coming here. I will connect it to this one. Okay. Another technique that I can find this go-to was signal routing. Again, you can find it. It's a go-to. It's a from. Both of them are available here, and you can select it from this one, or you can type it. If you know the name of the block, you can type it, and it's easily will find it for you. Don't worry about anything. Then the next one is that I need some display in order to measure, in order to show me what is available. I can go to the, for example, here there is some display that you can find it in the display area. In the sink, you can find that there is a display. Or if I don't know, I can, it's very simple, right here, display. Again, it will find it for me. Then I will click this one and I will connect it here. Then the next one is TO. TO is here. Look, when we are finding one variable like this one and we would like to save this variable here, we can save it as a local scoped or a global one. Then normally I am selecting global one because in the subsystem that I am using, all of them are use internal inside of these equations. Then I will click on the one, and this is the input one that you can find it here. Yes. Okay, now we make the first equations. As you can find it here, this is the first equation. TOC is equal, TO is equal to TOC plus 273.17. We need to make the T reference too. Okay, very simple. We can make the T reference. I will just Control C, Control and Control V, and I will put it here. Very simple. But this time I do not have any input. I know the reference temperature. Only I should add this one as the I should convert it from centigrade to Kelvin. Then that normally the room temperature is a 25 degree. I will add a 25 degree to this one, and then I will send it for this. Then it's become equal to T reference or the T ref, and it's a global one. It's okay. Then I keep it, and this is the display that we can find it here. Now you will find that there is some red shadow around of this block that later they will be removed from this one when we assign some input to them. Then don't worry about them and just move forward. Then by this subsystem in the PV array, as you can find it here, there is a thermal one, look, there's a thermal subsystem, and this is our PV array. Then in our PV array, as you can find here, we have some subsystem related to the thermal one, which is inside of this PV array. No problem. Our expectation is that the output from this array, like the real PV solar panel, is that we can measure one voltage and one current, and then we measure the voltage versus the current. Then the thermal part of the solar panels is inside of the PV array. The next part is related to IRS, as you can find it here. Now I will make IRS. Now to make the IRS, in order to make the IRS, I need to make another subsystem inside of the PV array. Then I will go through the PV array. Thermal part has been generated before. Now I need to create another one. Again, I will go to the subsystem, commonly used one. I use this one, commonly used. Then is there any subsystem? Yes, there is a subsystem. Okay, I will insert it here. And I will call its name. I should change its name. Its name is called IRS. But let me to show you something. If I want to make IRS, I will face with one denominator, which is called NS. It's made of a four constant, NSKATO, and all of them are inputs. We should assign them some values. Then just to make it more easy, I will make at first NSKATO, and in the next subsystem I will make IRS. Then easily I will change it to the NSKAT and O. I will make it in this way. I will go through this one. Right now I will remove this input output, and I will make this one. Easily we need some NS, which is a one input, depends on to the number of the series of the cells that we are using in the PV array. Then again, and K is a constant, A is a constant, TO is the what we found from the previous subsystem, which was the thermal subsystem. Now we need two constant and two input from the other subsystems or external side. Then I will again go to this one, and I have one which is called constant. There is a constant, we will put it here. This is a constant one, we will make it here. Control C, Control V, this is another constant. And we need to have in the commonly, we are using some go-to is not in the commonly. Okay, I will find it myself. This is a go-to block in order to find out this one. Okay, go-to block is the called ns, the number of the first one. Ns, as you can find it here. Yes, ns is the first one. I make it ns, then it's okay. The next one is constant value k. I don't know its value. I will go through the data sheet of the let's to go to find out what is the value of the ns. ns, for example, here it's mentioned, but we can assign the ns based on the data sheet that it's 72. Later I will add ns, but I will make it as a variable that I can play with this one and to find out the effect of ns in my output. Then the next one is a, and let me to check this one. This one, it shows that say k and a. Okay, k is 1.38 10 power. Okay, I will write it here. It's a 1 point, you can find it here, 1.38 e power minus 23. Then it's okay. I will consider this one as the constant, which is the k. Okay, this is a k. The next one is called a. It's a, as I understand. Yes, this is the, let me to check. Yes, this is a. Then I will call it a. And its value is important. We should find out what is its value. It is 1.3. You can find it. Ideality factor of diode, it's 1.3. Then I will write here 1.3. Okay, this is 1.3. And the next one is DO. This is the temperature in the Kelvin that we find it. This is the output of the previous subsystem, which was a thermal subsystem. Now we should multiply all together. Then I will go through this one and the math operations. I can use multiply, this add, division, product is here. Then I will select it. I will go through, oh, I did mistake, sorry. I will drag it and I will put it here again. But we need 4 terminal for this one. Then I will click on this one. Number of the inputs, I will convert it to the 4. Then I will open. I will put it here. Then again, the first one, the second one, the third one, and the fourth one. And the output can be considered as a one output that we can keep it as a from block. In the from block, you can find it here. And then this is the, we call it NS KATO. This is the output of this one. Then we will consider the display. We need one display. I will search it here, or I can go to the sync. I will say, oh, I didn't find, oh, I did mistake here. Then this is a display. I will go through this one. I will find this. Okay, display. I will insert it here, and then I will connect it to this one. This is a display. Control C, Control V. Then Control V. Then all available NS can be monitored, can be displayed here. Then this NSK, and I will go to check whether I am correct or not. Yes, NSKATO are here. All are available here. NS multiplied by KATO from the previous, and NS. Then just I should convert it to the global one. Okay. Oh, I did mistake. Its tag number is it is NSKATO. Then I convert it to this one. It's better to remove the under name here because the real name of this one is this one. Okay, then it's here. Okay. Now we have all of them. There's a no matching from, no problem, because later it will be. And like this one, it's no matching from this one. No matching. Go to blue because I didn't assign any number to this NS. Later we will do it. Then NS is finished. Okay, right now we need to make the IRS. We are ready to make the IRS. In making the IRS, we need to make another subsystems. Then I will go back in the PV array, thermal and NSKATO is already prepared. We are ready to make IRS based on these equations. In order to make IRS, we need again this output QVOC and ISC. Then I will go through this one, make the next one, then make the next subsystem commonly used manual. This is subsystem here. I will put it here. Then it's a 01. Then in this subsystem, at first I will change its name. Its name is called IRS. Okay. Then I will go through this one, and in the IRS what I need, I will go through the PDF file. In this PDF file we have one I short circuit, this one. Okay, then we need to have at first the Q. Okay, Q is a constant value as I remember. Yes, Q is 1.6 times 10 power minus 16. Then I will make a constant. At first I will find constant. I guess it's also available here. I can drag it here. The value is 1.6 e power minus 19. As if I do something correct, yes, 1.6 10 power minus 16. Okay, then it's the or constant, or we call it Q. It's better to write a name for this one. It's a Q constant. Okay, the next one is yes, Q times VOC. VOC is the input that you can consider this one as an input. Then again, we will come here and we will find the go to block. VOC. Product in product is here right now. Then it's this part now divided by, then we need one division, then we need one division divide, I will put it here, division, and we need one NSKATO. This is the next one. This is a multiply this one by multiply to this one. Okay. And then what is the next one? Okay, minus 1. We need one again, subtraction. Then we will come here. Where is the subtract? Subtract. In the math operation, we will come here. Okay, it's here. I will draw it here. It's a subtraction. But let me to check. Okay, at first I should apply the e power this value. Then before the subtraction, minus 1, we need to apply this. Then again, I will go to the function itself, the mathematical function. Which mathematical? Okay, math function. I will bring this one here. This is the exponential one. Yes, auto, the signal attribute. Yes, it's correct. The output is correct. Then it will come here. This is the output of this e power of this mathematical expression. The output of this one should goes to plus, and we should subtract one from this one. Then I will keep this as the 1, and then, or it's better to bring a constant here, commonly used. Then this is a constant 1. It's available here. It's ready. Then till here we make this bracket. Then I should make ISC. ISC is the input. I will consider as an ISC as an input. This is the ISC. This is from the short circuit current that we can find it from the data sheet. Then we should divide it. Okay, we need one division. We will copy paste here, one here to this one, and the other one to this one. Okay, let's move them a little back. Okay. Yes, this is the output of this one. Then we can find one output for this one. Then again we will find this is the from block. This from block, we need to keep it in the go-to. Then we will save it. What is the name of this go-to? It's called the IRS, and it's a global one. Then we press OK, and this is this one that we have. Then what you will find here, it's the way that we are making the IRS. Just to confirm what we did, ISC short circuit divided by this expression, this bracket. The bracket itself is a Q time VOC divided by NSKATO. It's available here in power e power this expression minus 1. It's a bracket, and this one, it's correct one. Then now we finish the IRS. Then we will return back to the next step. We should make the IS. We will go to make the IS. This is a PV array, the thermal one, the NSKATO, and IRS is already available. We would like to make IS. In order to make IS, we need to have this bracket and this expression, mathematical expression, which is exponential function. Then in the PV array, to making IS, I will go inside of this one, and I will make is. Oh, sorry, I write something wrong. I should write the subsystem. The subsystem. In the subsystem that I will try to find it. It is here. Yes, it's here. I will put it here. And in the subsystem, I will write this subsystem belong to is. Then it will go through this one. It is 0. And inside of is, we should start to make it. What we need in the is, you can find it here. We need TO over TR. Then again, we need some constant. Please save your file frequently. I save it right now. Then the next one is the TO over TR and TO over TR. Then we need TO, we need T reference that we have already made them in the other subsystem. Then again, I will use go to block. In the go to block, I will copy this one, Control V. Oh, sorry, I did a mistake. I should drag it. And this is the TO. In the previous one, in the previous subsystem, we make this one. I will have two of this one. One of them is TO, one of them is TREF. TREF is here. You can find it, TOTR, and then the next one is the division. We need one divide. I will press it here. It's a dy because TO over TREF, we have this. Okay. Let me to move it a little. Move it like this. Okay, this is a TO and TREF, and I will enlarge my screen. Okay, right now we can find it here. Okay, now what else I need? I need 1 over TR. Okay, then I will find a constant. A constant is math operations. This is a 1 1 1. Okay, then I will write constant. Constant is here. This is a 1. I will press it here, 1. Then I need again 1 division for here, and this is a 1 over TR. Let me to check it. It's a 1 over TR and minus 1 over TO. Then this is we need 2 of this one. Control C, Control V. Then 1 is here. I will connect it to 1, and I need 1 TR. TR reference is here. I will add it here. This is 1 over TR, the first one. The second one is 1 over TO. I will connect it to this one. This is a 1 over TO. Then we should subtract from each other. Then I will find out a subtraction. The subtract, then easily we can find the subtract. We will put it here, and this one is the subtract one. Okay, the subtract is here. Okay, this is this part that we have. Now look to the other part. Look to the other 1 over TR minus 1 over TO. QEG. Q is one constant that I show you before. Its value is 1 over 1.6 10 power 19. We have this Q, and we have one EG. EG is the value that normally it's made by the we can find it in the catalog or a data sheet of the. Let me to explain it where we can find it. It's in the data sheet of the producer or manufacturer. EQ. Okay, it's here. This is the manufacturing datasheet. Then we are looking for the EG. EG is here. It's a energy band gap. It's a 1.1. We have this one and we have Q. Then we have two constant and we will add these two constant here. It's a constant. Control C, Control V. We will put them here. Okay. Now, as we can find it here, this is the okay. At first, I will write this one. This is a EG, and its value is equal to 1.1, as it's mentioned here. It's a 1.1 electron volt. The other one is the value of the Q. Yes, Q, and you find before that its value is 1.6 times e power minus 19. Then we can make it here. Okay, we have these two constant value. We will put them together. What else we need? We need a multiply. Then we need a product. A product. The product. Yes, it's here. We can find it here. This is the 0, and this one is here, and this one is here. It's a product. The other two things is the K and A. Again, there are constants. Then we can copy and paste these two constants also, and we put them here. Then I will move them a little up, and we move these two a little up too. Then right now we have all together. What is this value? This is K. That it's a value that we know it's a constant. And the other one is A. Its value is equal to 1.3, and the other one is 1.38 e power minus 23. There are the K and the, yes, there are these two values that we can find them here. Then we multiply. Control C, Control V. This is the K. They should multiply them together. And as you can find here, Q times EG divided by K. Then we need one. Control C, Control V. We can put it here. It's this expression. Right now it's made here. Then we need to multiply to this expression, which is Ti over Tr. Then again we need to multiply. Control C over Control V. It's here. Then we will move it forward a little, and then we will multiply these together. Okay, right now we have this expression. Then we need to apply this to the exponential function. This is a mathematical operations. Then I will go to the math. In the math, there is one function here that you can find it. It's these equations. Then it's a mathematical one. Then what else we need? We need we make this part. We make this exponential expression. The other one is IRS time TO over T. Okay, TO over T are here, but we should multiply it to 3. Then again, we use the product, Control C, in order to make a cube. In order to cube this one, I make this one as a 3 inputs. Okay, then I will multiply these to multiply this, and it's a third time that they multiply together. The output of this one should be multiply to IRS. Okay, I will multiply these to IRS, Control V. But what is the IRS itself? IRS is one input that we can find it in the previous subsystem. Then we should bring one input and its name is IRS. And it's okay, it's IRS. Then this is this one, this is IRS. Then we have the output right now. Then what we need else, we need to multiply these together. This expression is made here, this expression is made in this part. Then we need to multiply them together, Control C, Control V. Then I will find out the output, and this output can be a store in one. This is a from block. In the from block there is this. Okay, go to, we can find it and we can assign it. What is the name of this one? It's called IS. IS is made here and we can find it here. Now we need to display this one. Then in the sync, if you are finding a display, it's not bad to find out this one and show this. This is the IS. Then easily again we can check it. This is IS, which is made from the IRS as an input, T over T3 power 3, and times the expression exponential of the QEG divided by AK, and all are available here right now. It seems that IS is correct. Then we will back to the PV array. In the PV array itself, we make till now the thermal part and SKATO, IRS and IS. They have already made. In the next part, we need to make IPH. Now we are ready to make the next expression. The next expression is IPH. IPH is inside of the PV array, one of the photocurrent element of the photocell. Then we will go through this one. Again, we make another subsystem. To make the subsystem, I should use the commonly used one. Then there is a subsystem. For this subsystem, we have one expression. I will remove this one and I will change its name. If you want to change the name, only click over this one. Then the next one is IPH. IPH is the photocurrent of the solar cell. We will go inside of this one. What we need, I will go to C. I need one I short circuit. Then okay, I short circuit is from manufacturer. Ki is a constant, again from the manufacturer. TO minus TR times G. G is input. It's a solar irradiance that we don't know. We should insert this one in order to start the modeling. Then this is the input that we will give it and assign it to this one. G reference is the solar irradiance in a standard condition, which is normally 1000 watt per square meter. Then easily we will go to make this mathematical expression. Very simple. We will start it by ISH. ISC. In order to make it, then we need one again. This is the one go to block should be here. One go to block is here. Okay, we will press it this one here. Okay, this part is, this one is called ISC. This is an ISC. Again, the mathematical operations, we need ISC based on this equation, ISC plus KI. Okay, KI TO minus T reference. Okay, then again, we go Control C, Control V, Control V. Okay, then this is a TO. And the next one is T reference, T ref. The next one is called T reference that we make it in the previous, in the thermal subsystem. Then we need to subtract. Okay, look, this is TO minus TR. We need to subtract. Okay, where is the subtract in the math operations? Here, subtract is here, then we will add it here, and we will put, and we will find this one. Then the output of this one should multiply, as I remember, to the Ki. Okay, then there is one constant, then we need a constant. If you do not press this key, it will not open. This constant is here. Then what's the constant value? It's a Ki. Ki, we should go to the data sheet and we should find what's its value. Ki is here. Yes, this is a 0.005254 ampere per centigrade. Okay, it's absolutely here. Then I will insert this value. This is 0. Everybody look, this is a Ki. This is 0.0000, and this is a 5254. Okay, that's great. Then I will insert it here. 5254. It's here. Then, as you can find it here, it's a 525 here. Okay, this is Ki. Then we need to multiply this one. We will multiply to whom? It was in the PDF file. Yes, let me to minimize this one. Yes, this is a Ki TO minus T reference. Multiply this one, then easily I will use a product. Okay, press it as a product, then it's here, then we will put it here. Then we will go, what else we need? We need plus ISC, then we need an add. We add them together. Okay, a little step forward. Then we will add these two expressions together. Till now we are here, Ki plus TO minus T reference, okay, plus ISC. Okay, this bracket is finished. Now we need to multiply to G over, we need to multiply G over G. Okay, we need to have one G. Okay, we have this one. This is Control V. This is the G. This is the input. Then we need to assign a number. Then it can be considered as input. And the other one is the reference G. Reference G is a constant. Normally, we have some constant value for this one. Then I will go to find it constant. In the constant, okay, the next one is the G reference. G reference is a 1000. Its name is G ref. gref and gReference are here, then we should divide them together. Then I will add one divide. The output of these two, this is a gReference over GG over gReference. Then it's okay, one side, the other side is coming to this, and the output is connected to the, and the output of this one is connected to the IPH. Then I will connect it to IPH and change the name to IPH. Don't forget, you should make it global variable. Okay. Now, as you can find here, only we need to monitor the values. Then it's not bad to have one display. This display is here. The display is here. The display is here. This is a display, one display here, Control C, Control V, oh, sorry. Another display, we can add it to this point. This is a short circuit. We need to monitor this one. And it's not bad to monitor the G value too, which is here. Then it's G values. Then now we should check again whether we are making IPH photo current correctly or not, which is equal to G over G reference. It's here correct. G as an input one, then we should make it as an input variable. K I TO minus T reference plus I short circuit. Then prefect, they are gather together, they are add together and then multiply. Then this is the IPH. Right now, the thermal, you can find here the thermal part, the IRS is made by the NSKOTO and IRS. IS is made here and IPH is also made here. All of them are available. The next one is making I. Now it's a time to make I. As you can find here, I can be easily generated by these equations, which is written at the bottom side as it is. I is equal to NP times IPH minus NP times IS times this bracket. In order to make I, again I will use the subsystem, and in this subsystem this is the I. Now I is equal to NP IPH, then we need to add some to use the go to block. In the go to block we are using one time. This is the NP. And the other one is IPH. Then we multiply them together by using the product. And also we need some other icons like the divide, product, and also look at this part. We will find we need also add. Then I will try to bring all of them which is available here in the math operation. We have also add. Then we use them one by one. Then there is a plus. They will be added together. Then this is NPIP minus NPIS. Then we need that we should use this is NC and V. Then this is the NP. We need another one which is equal to IS. This is the IS value. IS. Then they will go through the NSIS. Then the next one is NSIS times the expression of this one. Okay. Then we need multiply them together. There's a 3 input that they will add it here. This is the NS. This is the IS, and there's another one. The next items is QIS and NSQ. Okay. Then we have we need to have one input as a V. Then this is the V. It's available here. It's a V. After the V, we should plus it to add it to IRS. Then this is the V. The output of this one is I. This is our output. This is our output. This is IRS. And we need also RS. So we need to have one thing which is called RS. Control V. This is the RS. RS is here. Then we need to have one of them is equal to, let me to close this one. Okay. This is the V. What else we need? We need a Q. We need one constant, which is a constant. Then we have the constant, and this is the Q. The value of constant is 1.6 e power minus 19. This is the Q value. Okay, now it's equal to Q times V plus IR. SI is the output. Normally we have I here. Okay. IRS divided by NS. Control C, Control V. This one is NSKATO. This is the input that we can find it here, and then we have one division, and we have one multiply, which is the Q multiplied to V plus the output of this one coming to here, I times RS. Then again we need one I, which is going through the IRS. The output of this one RIS, IRS plus V, and it goes multiplied to Q, both multiplied to Q. Then they are dividing to NS. Then we need one mathematical function, which is the math operations. This is this one, it's a EU. Then it's coming here. Then after this one, we divide it by Q minus 1. Then it's a subtraction. We need a subtraction. This subtract. It's here. It's adding subtractions. Then it's coming here. It's minus 1. Control C, Control V. It is a minus. It's a 1. Then it goes through this. Sorry, I will remove this part, and I will go to the constant. Constant is here. It's exactly 1. The output 1 is here. Now the output of this one is based on this equation. This is the minus 1. It's going inside this exponential function minus 1, and then this is times IS times NP. Then times IS NP. Then we need to subtract them again from each other. It's Control C, it's Control V. They are subtracted from each other, and then there is its results is considered as an I. Okay, this is the output that we have. Now the output here it goes to input, that you can consider the I times RS. Now if we have the output I times RS plus V times Q divided by NSKOT, then e power this expression minus 1 multiplied by IS multiplied by NP. The output of this one minus NP IPH. Then it's become I. Then we can consider this one as the output. Then we need one output, and we need to submit, and we need to save the data here. Then again, this is the output here. Output. From this I, we need two output. One of them is the current, that we call it I. Let's come to the current, and also we can also keep the output in the sinks. We can keep it in the workspace for further action. We can keep it also as here as the output. Then we need again to have another output, which is the voltage that we implement, and this is the voltage. Then the voltage itself can be considered as the V. The voltage is here. We need also some display. We need also some display, that the display can show the output. Then we will keep the first one here, and the second one can be considered for the RS. Control C and Control V. This is our output, or no need. When this one is no need for this part. Now RS is available, then multiply to I again. Now it seems that everything is ready for the I. Just to check whether this is correct or not, we can find here that I is equal to NPIPH minus NPIS multiplied to Q multiplied to V plus IRS times the divided by NSKAT, then E power this expression minus 1 multiplied to IRS. Then it seems that I is absolutely now correct. Then we move back here. Now the loss expression is ready now. Now that we have made all of the subsystems and we finish all of these equations, we implemented all of these equations, now this is time to specify the input values. For the input values, we can go inside of the PV array, and for this PV array, we need to have some input. For example, we should consider operating temperature, what is the RS, what is the NS, what is the open circuit voltage, what is the NP, what is the G, solar irradiance, what is the ISC, short circuit current, and what is the input voltage. All of them should be specified as an input here, and we need to have two output from this PV array. This is what is our expectation from one PV array, that we give some input and we receive some output, which is voltage and current, and based on the voltage and current, be able to calculate the power. Now we need to specify these imports or the input ports. Then we will go through this one. We have already defined some input, and we should specify the parts right now. Then if we define these blocks like this one, we can find that for example, this is for T. This is this one can be considered as a input operating temperature in the centigrade, and it should be global. We can find it here. Now we need to have one input part, then the the input that we will define for this one, this is the input. Look, all of them are some input output. Then this input is called TOC. There are counted as the input. Okay, we will count this one to this. Now, if you go to the TOC, you can find that TOC, which is connected to the input, will be considered as the import and input of this PV array. We can repeat the same things, and for those variables that we need to specify, for example, this is RS, we can define this one as a RS, and its is called RS. Okay. The next one is if we consider the next one, what we have, NS, for example, RS, NS, it can be NS. We will change this one to the NS, number of the series of the cells. This is a NS and this is the one. Okay, again, it will be considered here. Then the next one, which parameters we need to define. This one is, for example, here, number of the rows or number of the parallel of the cells. Then we can consider this one as an NP, and the other one is NP. What about the next one? The next input. The next input can be, we decided about TOC, we find the RS. RS is defined, NS is defined, NP is defined. The next is G, G as an input. Okay, then we will change it to the G as an input, and we will change this one to the G. Okay, this is a press for a G. What else? What else? This is the short circuit current. This is something that is decided by the manufacturer. Then we should find it from for this part, I short circuit. Then I short circuit again should be considered as an input that we collected from the data sheet of the solar panel. This is our short circuit. Is there any things that we don't know and we need to insert? Only we should play with the voltage. Okay, yes, this voltage as an input. We change the value of the voltage and find out what is the effect of the various based on the corresponding to each V, which I is expected. Then this is the input V, and this one is V. But please let me to check whether in the last one, this is a, yes, this is a capital V, it's correct one. Then it's a V. This is the output. Yes, it's a output V. That's correct one. Then there are all of our input. Is there something else? I guess that we have TOC. Our TOC come down. VOC also open circuit. Oh, we did forgot this one. Then we should consider as the VOC. Then I will write this one here. Control C, Control V, and then this one is open circuit of the solar PV panels. VOC. Okay, all is here. Then VOC is known, RS is input, VOC is input, TOC is input, NP and S, IS short circuit current, and input V. Then all is correct. What is our expectation? Our expectation is current and voltage that we gave it. It means that we have this one, then it's good to have one output right now for this Then we are looking for an output port. Output port is here. Yes, this is an output port. Then this output port is considered as the current. It will be considered as the current, and the other one, Control C, is voltage. Okay, that's great. Then if now we are looking, you can find that we have these inputs and we have this output from our PV panels. Now we need to measure, we should give some input to the input ports, and we should receive some signal from output. Now this is a time that we were able to present some input for these ports TOC, RS, NS, NP, GIS, CV, and VOC. And the output of this PV array is the current and voltage. Then we need to present some sources. As you can find here, there are some sources like some constants. We can put it here. Then, for example, for the first time is TOC, then we can consider this one as a TOC, and it is connected to the input. The next one is RC, Control C, again, Control V, and this is RS. The next one is NS. We should keep them as an input, and this an NS. The next one is NP. All of these constants are considered here. G. Some of them are based on the datasheet of the PV array, based on that one that we are selected from the different manufacturing companies we can find from their catalogs. Then I assign it different value, and there are the parameters, input parameters, that we can play with them in order to make them as the variables. VOC should be, this is the V that we will consider this one. VOC is the one input that normally we will find it on the open circuit value that normally in a datasheet of the PV array is available. For V is the only parameter that we need to change it, variable its value from one constant value, for example from 0 to the higher value, which is maximum is VOC, in order to find out the relationship between the current and voltage. Then this one should be one variable. Normally we are using this ramp function in order to ramp function. Yes, we are using this ramp function. We put it here, we'll put it here, and this one should be here. Then this is the input that we call it is the ramp function. Yes, we call it the V as an input, and this one is VOC. Okay, VOC, it's here. Okay. Now we will start to connect them to the inputs. V is varied, IC, G, NP, NS, RS, and TOC. Now it's required to find out the output, but before that I find how it's possible to display the current versus the voltage. It's better to specify the value for this value. For example, for operating temperature in the centigrade, for example, we can select the 30 degree. We would like to measure the performance of this PV solar cell in a 30 degree. RS is something that we should find it in the datasheet of this company. Let me to find out. This is, for example, this is a JAP6 minus 72. This is a company multicrystalline silicon module for a JA solar company. Then the specification of this PV solar panel, which is JAP6, can be found here. All the specifications are here. Q, K, E, J, A, all are available. Then, for example, I am looking for RS. RS in this one is here. It's for example, series resistance of the PV. RP are here. Then you should find out what is the value of RS. What about the NS? What about the different value for this one? Let me to check whether it is mentioned before or not. Okay, then we can find that. Go to the catalog of this solar panel. This is from the JA Solar JAP6 by this number 72. 72 shows that it's a 72, as you can find it here. It's a 72 is the number of the cells and connections. Then NS can be found here, which is 72. Then let's go to this one. Then NS is 72. Then regarding to the NP, let's go to find out. It seems that the number of the cells that they are using here, okay, it means that NP not mentioned here. Then we can consider NP is 1. There's not so many. Yes, this is NP is equal to 1. NP is written or not written? Not written. Okay, it's not mentioned. NP is considered as a 1. And then NP is 1. G, it depends on to the which solar radiations. For example, assume that it's a standard one, it's a 1000, or we can consider this one 1201, okay, because the reference one's 1000. I short circuit. Again, we should go to the data sheet of this panels. I short circuit. This is for this one is for 72. 305 to 325, 305 to 305, all of them are available here. We can find here the I short circuit versus the current one. For example, we can consider for GAP672320. For example, assume there are different. This catalog is for these 5 models. We can select 305, 310, 0, 315, 320, and 325. Okay, then assume that, for example, I short circuit for this one. This one is a good one. Maximum power is 18. Module efficiency is 16.51. Okay, we will select this one. Then the short circuit current is 9.06. 9.06 is 9.06. 9.06 ampere is the short circuit. Okay, what about VOC of this one? Again, we will go to the VOC. VOC is here for this model is 46.22. Because I selected the 320, it's a 9.06. 9.06. Then we will go to the VOC is equal to 46.22. Okay, what else will remain? This is TOC, this is RS. RS, it doesn't mention. Let me to find NS is fine, NP1, then G is 1200, ISC is 906, and this is 46.22, except RS. Let me to check. Now let me to check. I couldn't find RC. I am looking for IS, the series resistance with this photovoltaic cell, multi-crystal line 1. Its RS is not mentioned. Then it's better to contact to this company, to this sales office, by this email, and ask them what is the RS. This is the most accurate one if we cannot find any information regarding to the RS and the RP. But look, there's we do not need RP, but we need RS. Then we should contact the company because I didn't find it here. Okay, now let's go and continue, and we will consider one value for this right now. For example, we can consider its value is 0.18. It's a normal range that we can select it for the most of the solar panel, but the accurate one should be found through the company and through the manufacturers. Now we have one output current and one voltage current. Then we need one display oscilloscope. Then we can go to the source in the sink. In the sink we can find one oscilloscope. We can put it here. Then I did mistake. We need XY graph because it's a voltage, current versus voltage, and the other one is like this. Okay, I will put it here. One of them is voltage as a X and current as the Y, because we would like to draw the current versus voltage. This is voltage versus current. The other one is that we have the current. Current should come here and multiply to voltage. Then again we need another one. Then this is let me to make it smaller. This is the I change it to the IV, and the other one needs to be here. This is the This is a power versus voltage. Okay, let's go to see what will happen. This is the voltage one. Then again, the voltage should come here. The voltage should become here. It's this one. And the other one is multiply of voltage, then product. Then the product is available here. Yes. Then the product is here, voltage times current. Then we can consider one, the voltage times current. It's become the product, it's a power, then we'll give it to this one. We can also consider the display. The display is here. One display in order to find out the real value each time. Okay, this is for our display. Now it's better also to do some setting. The minimum X value is 0. The X maximum is about 60 volts because this is a voltage. Y minimum is 0 and Y maximum is about 20. And it's okay, the rest is okay. This one is also X is 0. X maximum is the 100. Y is 0. And the maximum power is about 700. Now it seems that it's ready and we have our module ready to run and we need to run it. Then again I check the input value in 30° by this value of RS and S and P, G, ISC, and this is a ramp function that it will varies, and this is a 46.1. Then now it's ready to run these Simulink models in order to find the efficiency of PV array. Now it's a time to run the simulations. As you can find here, we can close this library right now and we can find this module which is ready. There are some inputs that we give it and then we would like to play with these inputs. We can change the temperature to find out the effect of temperature. We can play with the solar radiance and find out what is the effect in our output. Now we will run it. In order to run the Simulink, we can push this green run button. Then as we run it, you can find here that there is something like this. For XY, it means that it's a power versus the voltage, and the other one is the current versus the voltage. Okay, let's go. It seems that it's not reaching to the maximum coming down or like this one, because normally, as you can find here, we are looking for some kind of the behavior like this. Look, this is the voltage. This is the voltage current versus the voltage. We are looking for this behavior in this, and the other one is the power versus the voltage. Then if you are looking to the, we can find that we didn't reach to the maximum value in the power. Then one thing that we can do is that we can increase the running time here, because it's a voltage is you can find here in a ramp, it's a starting time, input time, then it's related to the time of simulations that we visit. This one again, you can find that it's moving up, it's a power, but it seems that something strange, that there is something like the 60, even past the 60. And look, if I change it to the 1000 or for example 500 second, what will happen? Oh, again it seems that even it move out. Then let me to increase the limitation of this one. For example, for the voltage, we can run it to 600, and for the uh, current, for example, 200. Let's to see what will happen. The other one is the voltage, for example, 200, and for the power 1000. Let's to see what will happen. Oh, again, it seems that something like this. Then it seems that voltage, no need to increase the voltage to the 200. It's enough for this one. Yes, it's a current one. Current cannot be increased. Then let me to check something is wrong in this one. One important part of any simulating program is a debugging and finding the problem. Then we should work enough in order to find out what is the problem in the and finding out the errors. And it depends on to the skills of you and me in order to by doing more practice and practice to find out the problems. Okay. Then this is an important part of the running of the simulation to find out and debugging the problems. Then again, x can be y is it was enough about it's okay, we will keep it as it is. It seems that it's not related to the timing, then I will keep it, for example, 50. Again, okay, you can find here that there is some problem because the y plot for this panel cannot reach to a real value. It's near to this panel itself. As I remember, it was low power one. Let me to check it. As I remember, the maximum power 50, 100, 150, 200, 250, 300. 350 is the maximum. It seems that by the different in this standard solar radiance maximum we can reach the 350. Let's do what's the problem that we are going in this way. Oh, there is some warning here. Okay, let me to check the warning. There is a 4 warning that you can find it here. Let's to go to find out what is the warning 1. Then this is the related to the first one, matching go to from. Let me to go. Oh, this is related to I. I is here, one of the subsystem. It seems that in I there is one problem in IS. Let me to go to the IS to find out what is the problem. IS, oh, IS here, and it's a problem here. As you can find here, it's a red shadow around of IS. It shows me that there is some problem. Let me to check what is this. No matching from block. Okay, let me to go through this one. Wow, the problem is here. It seems that is should not be a local, it should be a global variable. Then I keep it as a global. Okay, then run back and run it again. Run it again to find out whether the problem is solved or not. Then now it's ready to run. Oh, it's here, it's here. It's like this one, it's available here, and the other one is here. Okay, it seems that now the problem is solved. Now it's coming down, it's here, its behavior is like this. Then let me to change. It means that the maximum it can be about 20 in the I. In the I it's maximum 20. Then in the Y I will change it to the 20. And I guess that it should be enough to be 60. Okay, and the other one, it seems that, let me to check whether what's the value for this one. 454 voltage. Then power 400 is enough, and the other one is for example 100, or this is a Y one, no problem. We'll run it to find out what will happen. Now I will close this one, I will close this one, I will close the dialog. Okay, let's go. Okay, it seems that still we need to change the plot. Okay, this is a 50 and 100. We can change it again in the I versus the voltage. Okay, it's a 50, it's good one. And the other one is also, it was 50, I guess it's enough. Then both of them 50 and 50. Okay, this is the relationship between the voltage and current that we have this one. Easily, if you want to find out the effect of each of them, then it seems that the maximum current in 1200 is something like this, and this is the maximum power that we can reach it. If we play with these other parameters, for example, if we change the temperature. Now, if you are looking, it's the voltage. If you don't mind, I will change the current itself, the values of the current. In the Y, it's about 15 for the current. For the current, it's a 15. Yes, it's a 15, and this. Now, if you are looking, it's about 11 ampere, and this is the VOC that we can find here, the VOC open circuit voltage, and this is here. Now, if we play with each of these parameters, for example, if I change TOC to, for example, 10 ampere, 10 degree, let's to see what will happen. Then 10 degree, this is about 11 current, and it is about 350. If I convert it to the TOC, you can find, okay, the voltage will, the current, but it seems that VOC will increase. It's great. Then lower temperature, as you can find here in the normal graph, you can find here, I guess the effective temperature is not shown here. This is here. By decreasing the temperature, VOC will increase, and it was something that we can see this one. We should increase the boundary of the voltage VOC in our graphs. Then increasing the VOC, I will increase in the first one VOC, I will increase it to, for example, 80, and also in this one, this is again 80, and run it again. Okay, it seems that the power also will increase. Okay, we need more, and also we should change the time. Then I will increase it to the 100. Yes, 100, but just to see the power plot, it's required to increase this one, for example, to the 600 as a power range. Then we can find it that it's again working perfectly. This is a power versus the voltage, and at this point it shows the VOC, and this is the current versus the voltage. And I guess that in the previous curve that I showed you, this is a current versus the VOC, and this is the power versus the voltage. This point is VOC, this is the maximum voltage. This is the maximum voltage, and it's possible to find out the maximum operating point. You can find it here. The maximum voltage and current, I short circuit, and PM, and this is a VOC point. That again, we can find all of them here. Then I guess it's a good practice for all of us to run our programs and to find out the errors in order to find out the characteristics of our PV cells by changing the different variables. For example, here I change and I played with the temperature. Next time I can play with the, for example, increasing the 1600 watt per hour, and to check what will happen. Yes, you can find here now again that the current is increasing. From 11 has been increased. It's obvious because the solar irradiance directly proportional to the generated current, and it's obvious one. If I increase it to the, for example, 500 watt per hour, you can find that again. Okay, there is a current versus power. You can find that how small is the current. Easily you can draw the effect of the solar irradiance on the current versus voltage curve and power versus voltage curve, and to see each of them. For example, if you increase the ns, the number of the cells, what will happen? Increasing to the 100. Again run it, again run it to see what will happen. You can see again that a little has been changed. For example, now it's a 4, it is reaching to the 150. If I play with any other parameter here, we can find its effect. Now it seems that everything is completed, and now you can run your own projects by the different modeling. Then be careful that depends on to the type of the solar cell and the type of the structure and crystalline that they are used in the solar cell. You can develop the, again, using the equations, different part of equation implemented in your modeling, and find out the behavior, especially the power versus the voltage and current versus the voltage of your solar cell. I hope that this video will be useful for you, and enjoy it.